Hi everyone. So if you have ever wondered whether you can extend the operating system's functionality without having to recompile the entire OS, then it's actually very simple. And I'm going to give you a quick overview of how to do that through a mechanism called kernel modules. Almost every major operating system allows you to extend its capabilities in a modular fashion. And almost any third-party developer can write kernel modules to implement their own required functionality. So let's take a look at what are kernel modules. So as I mentioned, kernel modules allow code to be added to the kernel dynamically. What that means is that if your OS is already running, then you can insert additional pieces of code into a running kernel that add extra functionality to the kernel. For example, you might have a special hardware device. Let's say you just bought a webcam, and in order to use the webcam, you might need certain functionality inside the OS to talk to the webcam hardware. And the developers of the webcam would have uh, provided you with a kernel module to add that additional capability. So the one of the benefits of having kernel modules is that you only need to add the functionality that you're going to use. You don't have to load all possible features that are not required at the time your operating system is running. And you can delay adding kernel modules till the point when you're ready to use that particular functionality. So, so as a result, just because you modules allow you to add the bare necessary functionalities into the kernel, it reduces the overall kernel size and the memory footprint and resource usage, and it just allows your OS to be more slim and run faster. And another benefit is that any third-party developers who are not part of the core OS development group, they can develop their own kernel modules and make it available. And anyone who needs that functionality can download the modules and insert it into their kernel. Okay, so let's take a look at a high-level diagram of how kernel modules work. So on the right side, you have the core kernel, which implements the uh, absolutely essential functionalities for the OS, and these include things like memory management, CPU scheduling, and all that stuff that comes pre-installed and statically compiled into the kernel. But the kernel proper also provides certain hooks through which additional uh, software can register themselves and add extra functionality. So, so on the left side, we have a kernel module developed by third party, which we want to dynamically add into the kernel. So one of the first things you do is you insert a compiled kernel module into the kernel, uh, and when you do that, then the operating system would invoke a special routine called an init module. Just like for a normal C program, you have the first piece of routine that runs is the main function, right? So similarly for a kernel module, the first piece of function that runs is the init module. And in the init module, you can do all kinds of initialization to get the module ready to do whatever it's supposed to do. Normally, most modules, what they will do is they will tell the kernel what kind of capabilities they bring. For example, they might be handling a character device, or they might be handling a block device or a network device, or they might be improving certain aspects of the kernel's functionality, like adding a new file system and so on. So the core kernel, when it receives a request to register a capability, then it would record that capability somewhere in its internal data structures. And these capabilities differ from one functionality to another. For example, the capabilities for adding a device driver may be different from capabilities for adding a file system. So once these capabilities are registered, you might be wondering, what are these capabilities? These are basically function pointers that the core kernel keeps track of. And these function pointers point back to the code that the module brings with it. So as you can see from the red arrow, that the function pointer will point to a function that's implemented as part of the module. So whenever a user invokes certain functions that require the capabilities used by the module, the function pointer would be used to invoke the module's functions. So uh, so during normal operation, the kernel will make callbacks into the module to invoke the registered capabilities. The modules may in turn call back core functions from the main kernel to use certain capabilities provided by the core kernel, and so forth. Right? So, and that's how the module works. Module is not something that keeps running all the time. It basically gets inserted into the kernel, and then the kernel invokes module's functions as and when needed by the kernel. And at some point, like let's say you're done using a kernel, you want to remove the module from the kernel for whatever reason, then then at that time you would when you remove the module, then you have to the module has to leave cleanly. So as a result, every module should implement an exit function, or here it's represented as a cleanup module function, and the cleanup module function would unregister its capabilities that it registered earlier. It will free up memory that it had allocated, and all those things. All right. So this is a high-level view of what kernel modules look like and how they interact with the core kernel. I would quickly give you an overview of how you can write a simple kernel. Normally, when we write a new programming, when we learn a new programming language, first thing we learn is how to write a hello world code. So here we are going to write a hello world module, and the code for this module is available at the link on this slide. And it's a very simple module. As you can see, it has just two functions, init and exit. There are a bunch of headers in the beginning. There is a license code. Different modules can have different licenses, open source license, a proprietary license, and so on. And then we have two statements at the end which tell the core kernel what are the initialization and exit functions. In this case, we are telling the core kernel that the initialization function is called hello init and the exit function is called hello exit. So when we insert the module, the kernel would call the hello init function as initialization routine. And in this case, we don't do anything. We just print something onto the kernel console. So you might notice we are using something called print k instead of printf. So print k prints to the console, which is where all the kernel's messages go in, the system level messages. So this is unlike printf library routine. Here we have a kernel level routine called print k. And then in the exit module, again, when we remove the module, the exit routine gets called, and again, we print another message to the kernel console before exiting. All right. So, so what do you do with it? Here, you have to compile the module. So there, you need to have a makefile. Makefiles for module have a special format, and I'm not going to go into the details of how the makefile looks like and the format, but you can find a lot of information at these two links. But just for simple module like this, you could just copy the makefile that's listed, and then use the make command that's listed here to compile your module, and then you will get a kernel object file hello.ko. That's what you would insert into the kernel. So how do you insert a module into the running kernel? You have to use the insmod command as shown to insert the module. You will notice that we are using the sudo option to acquire root privileges. In order to insert module into a running kernel, you have to have root privileges, because once you insert a module into the kernel, it is part of the kernel. It has full privileges of the operating system. So you need to have root permissions to insert your module into the kernel. So what does the insmod do? It takes the binary of the module hello.ko in our case, and then it would the insmod command would internally make a system call for sysinit module, and sysinit module would allocate memory for the kernel module using vmalloc, and then it would copy the binary that we provide into that allocated memory. It would map kernel references by matching the functions that you call in your kernel module against the kernel symbol table. And then once all that is done, the module is ready. At that point, it would call the module's initialization function that we mentioned earlier. To remove a module, we call the rmmod command to remove the module, and that would call the exit routine for the corresponding module. At any point, if you want to see in your system what are all the modules loaded, then you use the lsmod command to check the module. So internally it will check a location called /proc modules. It's part of a pseudo file system, and it lists all the modules that are currently loaded in the kernel. So there are certain things to remember. Kernel modules, when you're writing code for these are not these are somewhat different from user level programs. In user level programming, so you have access to things like C libraries, but then in kernel you don't have access to C libraries. Instead, kernel provides its own set of functions that you can invoke for general purpose operations, such as printk for printing to the console, kmalloc for allocating memory, and various other versions of malloc for that have different internal differences, kfree to free memory, and so on. So as you get more familiar with kernel programming, you would learn all these internal APIs of the kernel. And then kernel itself exports these APIs to modules. So if you look at the kernel code for the Linux, you would see that there are export macros available that export certain functions for modules to use. So likewise, you don't have any standard header files that you use in user space. Kernel has its own set of internal header files that you need to be familiar with when you're writing your module. Another aspect deals with bugs in kernel code. So when you're writing a module, you have to be careful because any bugs in the kernel can crash the entire kernel. With a user space program, if there's a bug, it will only terminate that particular program, or it will make that program misbehave. With a kernel module, the entire kernel can misbehave, which will affect all the processes in the system. And finally, there is version dependency issues. The modules that you write have to be compiled against specific version of the operating system on which you want to run. So, so when you compile the kernel module, it will by default compile against the currently running kernel, or you could specify other versions of the kernel that you want to compile it against. And this information gets hard coded into the binary for the module. There are important issues that to keep in mind regarding concurrency. Inside the operating system, pretty much everything is affected by concurrency. So as we saw earlier, that once you load the module code just sits there. It doesn't do anything till the operating system's code invokes the handlers that we register during initialization. So all the different parts of module, different functions of the module can get invoked concurrently, meaning that they can either be invoked from the context of different processes, they can be invoked simultaneously on different CPUs. So any code that you write has to be mindful of these concurrency issues. So if you have a data structure in the kernel module, you have to be mindful that different CPUs may be modifying the same data structure in parallel. So again, you have to use correct synchronization mechanisms to make sure that your modules behave correctly when it's being invoked concurrently. Your module code can also be invoked through interrupt service routine, especially if you're writing device drivers. A hardware interrupt can trigger a sequence of kernel calls that can finally end up at your modules function where where your code may be executing in the interrupt context. So so that's another thing to keep in mind. You can Also set up timers to invoke certain functions of your kernel module. Again, that's similar to being invoked through hardware interrupts. And then again, on multiprocessor systems, if you have multiple CPUs, then different parts of your kernel code can be invoked from different events. So as a general rule of thumb, your module code should be what's known as reentrant, meaning that if any module function is invoked multiple times concurrently, it should behave correctly. If any particular data structure is modified by different functions, then it should behave. Your module should still maintain correct execution. This shows some of the general rules of thumb for writing initialization and exit routines. So we have the initialization routine on the left hand side, where your initialization routine is responsible for registering a bunch of capabilities with the core kernel. So registering a capability with the core kernel can fail. For example, if you are inserting a new file system, and let's say there's another module handling the same file system, then that initialization can fail, and your code should be able to check for errors and handle the initialization. If you're registering multiple capabilities, then and one of the capabilities further down the execution sequence fails, then instead of simply throwing an error and returning, you have to first unregister the capabilities that you had registered earlier. So in this case, if you're unable to register those capabilities, then you have to go back and unregister this and that capabilities. And likewise, in the exit cleanup function also, you have to unregister everything that you registered with the core kernel, right? You can also provide parameters when you are inserting a kernel module, just like you can provide arguments to a user level program. So it's slightly different that you have to give names to each of the arguments, and the arguments are specified as a key value pair. So in this case, there's another version of the hello world program where we are passing two arguments, how many and whom, and then when these arguments are provided, then in the module would print, for example, hello class 10 times in this particular example. The corresponding code for passing arguments, you have provided a link to that. Feel free to download it, compile it, try it out. I just want to talk a little bit about different types of devices, and particularly character devices. So if you look at all the different hardware devices that your computer might be handling, they can be broadly classified in three categories: character devices, block devices, and network devices. Character devices are those which perform input-output 1 byte at a time. Examples of character devices are your keyboard, your mouse, even the display screen. These are generally character devices, and the property of these devices is that there are no discrete message boundaries in the input-output. It's just a sequence of bytes that user level processors can read and write. In contrast, you have block devices where the input-output is performed at a message granularity. For example, a hard disk is a storage device, or any storage device for that matter. These are block devices. And when you read and write to these storage devices, you read and write chunks of data, which are called blocks. For example, 4 kilobytes of data at a time. So these have discrete I/O boundaries, but not just that, but the size of the I/O is fixed. For example, you write 4K or 8K bytes of data on storage devices. And then the third category is network devices, which are a combination of which have a combination of properties of character and block devices. So here you have discrete message boundaries, like in the case of block devices, but at the same time, the size of those messages is not fixed. They can vary. So it's with network devices, you can send and receive packets that can be of different lengths, but each packet is treated as one I/O unit. So in addition, there are other meta classifications of different types of devices depending on the underlying technology. So you can have a class of devices under USB or SCSI or FireWire and so on. And these all differ in terms of their specific properties, how much data they can handle, how much power they consume, or what kind of bandwidth they provide. And you can implement the first three types of devices, character, block, and network devices, under any of these classes. For example, you can have USB devices for storage, or USB devices for keyboard and mouse. The first for storage, those are block devices. For keyboard and mouse, those are character devices. So if you want to write a simple character device, to get started, Linux provides a category of devices called miscellaneous devices, and all devices have a major and a minor number. I won't go into the details of these here. It's just a way of identifying a specific device on which you want to perform I/O operations. So miscellaneous devices have a fixed major number 10, and then the minor number is assigned to them dynamically depending on what is available. So you don't have to guess as a user what major and minor number you want to assign to your device. And here are some programming details. It's a very rough sketch, and there are certainly many tutorials out there. But one of the things you have to do is you have to declare a device structure in your module, as shown here, and we just specify that the minor device number is misc dynamic minor, and this tells the kernel, go pick a minor number for me. I don't know what to pick. You can give a name to it. And then finally, you have to provide a reference to file operation structure. In Unix, as we learned before, everything, files, any I/O devices, are accessed through a standard virtual file system interface. So we have to tell the operating system what are the file operations for this particular device. So in this case, we have to then declare the file operation structure, where we specify who is the owner of this uh, uh, device, and then what are the different operations. In this case, we are supporting open, close, read, write, seek, and so forth. And we have to initialize the function pointers for each of those operations. So the purpose is that when we register this device with the kernel will know which functions to call on your device when a user performs an open operation on your device, or a close or a read operation. So so here's an example. So we are if you have an open operation from a user level process, it would call the misc open function that we had registered earlier. Or if you perform a read operation, then it will call the misc read function, and so forth. Okay. So how do you register your device once you have declared those two structures? You register your device with the core kernel in the initialization function. Here we skip a lot of the other code just to show the registration operation. There's a kernel provides some miscellaneous register operation to API to register a character device. You just pass the device structure that we declared earlier as an argument to this function. And likewise, when you exit the module, when you remove the module, the exit routine gets called. There you deregister the device again by passing the device structure. So that's not enough. You also need to implement the function pointers that we declared initialized in the fops. So here is an example where we are implementing a function pointer to perform a read operation on a character device. Again, the details of specific read operation will vary, but generally you would pass some data back, copy some data back into the user buffer that's passed as an argument. So generally, when you're sending data between the kernel and the user space, you have to use certain kernel APIs to pass this data. You can't simply use memcopy like you do in user space. So here, if you're sending data from kernel to user space, you would use copy to user. If you are reading data from user space into the kernel, you would use the copy from user function. And the reason for doing this is that the kernel data and the user space data memory would are sometimes in different segments, or they may have different memory permissions, or sometimes even in different address spaces. And these can vary from one kernel version to another, from one processor to another. So you don't want to worry about these details. The copy to user function will take care of architecture specific and version specific details, and it would make sure that your data is copied correctly across user and kernel spaces. I mentioned a little bit earlier about memory allocation. There's a kmalloc routine. Unlike malloc routine in user space in the kernel, kmalloc routine is available. It allocates a physically contiguous memory region. If you're allocating a lot of memory, this can sometimes be an issue to find physically contiguous region. So there's only a limited amount of memory that's available through kmalloc. And then if you want larger memories that can be paged, that can be virtually contiguous but not physically contiguous, then you can use vmalloc. Uh, so again, if you look at kernel documentation, there all these the details of these specific allocation routines are explained there. So I won't go into the details here. Here are some additional references about the GNU general public license. So whenever you write open source code, then you have to specify what kind of license, what are the rights of other people to copy your code or distribute your code or modify it. So GPL is the most common open source license, but there are many others out there. All right. So hope this was useful, and hope you can get started with your first kernel module. Good luck.